Hello everybody. Today's class is about the theory of graph neural networks. So let me start with the theoretical connection between GCN and the spectral filter. So basically, it is the same as the previous lecture. So we already understand about the input of GCN right now, and it is computed from this, and based on this, when we ignore LALU activation function, so one layer GCN is the same as this function, and we from the initial feature, and we multiply by the L normalized L, and we multiply by the trainable variable matrix, and we get the prediction. From this perspective, the spectral graph theory is presented like this. We talked about it is actually learning eigenvalue filter, and it was computationally expensive. By using the recurrent Chebyshev expansion, we were able to compute summation of the k number of terms, and each term is computed from the previous two, the LTs. Then L is from another version of a normalized population, and it is multiplied by the TP minus 1 and TP minus 2, and they are computed from this. So it is the initialization of the T0 and T1, and we were able to compute this. So it is fast. So we were stopped at that point, and so actually we were missing the actual connection between the Chebyshev expansion and graph convolutional neural network. So this one was from the previous slide, and once again we got this. Well, we assume k is equal to 2, and we got this. And from the initialization from T0 and T1, and we also assume that the lambda max is equal to 2, we got this. And we just assign x to here, Lx to here, and we get this. And we put the L minus 1 here. So it is just the mathematical derivation. And well, we also assume that this, and we also introducing the theta. So we don't use different theta for the different t terms, T0 and T1. So we just assume that they share the parameter, and we also made the x toward the r side of this bracket, and we are able to get this. So this is actually they're very familiar with, right? by using the renormalization trick. So we substitute this one to this one. So they are mathematically not the same as this one. That's why we call this is the trick. And when we put this to here, that is actually the same as this is the Z, and this is the same as the GCN. So this is a one layer GCN, so without the LALU. So now we are able to see the GCN is the approximation of the spectral graph theory, and it assume it is considering the two hops in the Chebyshev expansion. So that is a theoretical relationship, and the actual GCN paper compared to the Chebyshev expansion with the different case. So we have talked about 2 weeks ago, and GCN was better in 3 data sets. So that was the initial the theoretical property of GCN, and now we understand more about the graph neural networks. We will talk about other theoretical properties. So let's start with how powerful the graph neural networks are. So the paper, the iClear 2019, the authors are talking about the expressive power of GNNs, and they found that it is deeply related to the graph isomorphism test. So the question is, am I able to use my graph neural networks to distinguish two non-isomorphic graphs? So this is the question. So GNN is capable of many downstream tasks, right? Node classification, link prediction, and others. And we may use the GNN for the isomorphism test. When it is able to do this, so the capability, the expressive power could be used for the node classification and link prediction. They are deeply related. Because when we are able to distinguish two different graphs, and which means we're able to identify two different subgraphs or nodes and many across many different partitions of the graph, and we are able to learn their different at least structural aspects, right? So that's why it is a very good start to think about the expressive power. So this is the one of the famous isomorphism test to see the graph is the two graphs are the same or not. So which is called Bisphyler-Lemon test. So it is a simple but powerful way of distinguishing two graphs. So the procedure is following and this algorithm. So we pass the random hashes of the sums along the edges. So we have the initial node coloring. So we assume that each node of the graph has some color like this. The output is to get the final node coloring. So we assign different colors at each iteration. So with respect to the vertex, we assign different color from this hash function, and we increase time step until the stable node coloring is reached. So we assign different colors based on the neighborhood. So it is considering the neighborhood. And we see the coloring, the coloring in jar stable or not. So in this case, to consider the neighbor, here we use a summation, the summation function, but in actually it is the same as a concatenation, and it is much generalized version of the bias by the lemon test. From the color of the neighbor node, we concatenate the colors and combine with its own color, and we assign the new color. So to assign the new color, we use the hash function. Let me give you the example. So now we call the bias by the lemon test as WL test, which where we yes, here we also assume that the color representation, so we use just one color for the each color, and then we can call this the isomorphism test as WL1. So here we use WL1. So we have new input. So this is from the label graph. Each color represent the different nodes, and currently we use the same ID for the different nodes. So here we have two different input graphs and try to identify they are the same or not. So at the first iteration, from this is the same as this one. From this, by looking at the neighbors of the first node, we summarize the nearby node's ID as like this. So it is surrounded by 1, 1, and the node ID is also 1. So we put 1, 1, 1 in here. Similarly, this has the 2, 1 neighbors. He will assign this. I'm sorry, so in this case, we're not considering the self node representation. So in this example, it is from just neighbor. So it has 3 edges, right? And the blue node has 2 edges. We assign this, and the yellow node has 2 edges, this and this and this. And similarly, we can create the tuple from the neighbors. And then, so this is from the previous slide, we can hash from this tuple from the 1, 1, 1. We assign different ID because one is used in the previous iteration, and in this example hash assign something like this. So for 1 1 you assign 2, 1 1 1 we assign 3. So with this way we have different 2 3 2 2 3. So now we are able to get the hashed labels, something like this. We keep iterating the same procedure. So we see the neighbors, and the 3 is surrounded by 2 2 3, and this is surrounded by 2 2 3. We are able to create the tuple. Now we get this. So we assign another the hashed label from the 2 2 3. You assign 6, and 2 3 you assign 4 3 3 you assign 5. We got this. And we also iterate the tuple creation in labeled hash step once again. Now we are able to get this. In every iteration we see the coloring is stable or not. When we compare the coloring from, so in this case the hashed label assignments are stable or not. We see the assignments are stable or not. Compared with the hashed label from C2 and C3, we see they are stable or not. How would you do that? So this is a very interesting the implementation issue. So one of the implementations could be from the C2 we have now we have the 4 5 6 are used for the G1, right? G1 means the graph 1. So how many 4s are here? We have 2, 1, 6 are 2. So what about at C3? So we have 7, 8, 9. So these are the hashed label. When we count their occurrence in the graph 1, we have 2 7, 1 8, 2 9s. It looks they're not changing. So you have same the color count representation from G2. So by looking at this information, we are able to conclude the stable node coloring is reached. So here we use now called stable node, the hashed node label is getting from the final iteration. So and we stopped learning, and we see the two graphs are different or not by looking at their actual the hashed labels. So in this case, two lines are connected. You can delete everything. Clear page. So 9. So 9 is, this 9 is connected to 9 and 7. 9 and 7. 7 is connected to 9 and 7. And 8 is connected to 9, 9, 9. 7 is connected to 7, 9. 7, 9. So in this case, we can conclude that they are the same graph. So this is the example of the WL1, the isomorphism test. So now we understand what the WL test means. According to the paper, they showed that GNNs are almost as powerful as the WL test. But their important assumption is that the graph use discrete node features, and the GNNs can only be as powerful as the WL test. That is the one of the important assumptions. And for the maximal power, the maximal power is to have the expressive power of the WL test, and that is the maximum power. The important condition for the power is to use the injective aggregator.